We're going to be presenting on generative adversarial networks today. Hopefully you're in the right place. So this is a topic that we're both pretty excited about. We've been working on a project for about 2 months now that involves the algorithm. And recently stuff started working, so that's awesome.
Do you know where the star files are?
So I guess to answer your question, not that. But yeah, we have a GitHub repo. If you go to the ML Berkeley organization on GitHub, you can find the first repo on there, on that list, should be the one related to this workshop.
GitHub.com/mlberkeley?
Yeah, github.com/mlberkeley/ I think GANs workshop. Wait, Daniel, don't close that. No, don't close that.
Can you from the back when you have the mic?
Yeah, I'll try to set that up. You think I can just speak up? And this is a lot harder to set up than I'd like. Okay, cool. Yeah, we'll try to speak up for people in the back. Okay, so yeah, go to our GitHub repo. Starter code will be relevant about halfway through. It's really just running through some like training code. We'll kind of step you through it as we talk about it, and yeah, hopefully we'll be all good to go from there. So, quick intro about us. I am a junior in EECS. I'm also part of MLab, and that's me on the left.
Yeah. I'm on the right. I'm a freshman in EECS, and I'm part of MLab as well.
We're both named Phillip.
Okay.
Surprise.
Jason, it's all.
Yeah, exactly. So, we're going to be teaching you about GANs, and this is a really cool result that came out about a month and a half ago from NVIDIA. And so what they're able to do is create like really high resolution images of celebrities that usually look pretty good. And then by using a technique that's very available to GANs, they can do these kind of cool face interpolations, which end up pretty trippy. Cool. But before we get into that, we're going to have an introduction into deep learning to kind of get everybody up to date on how deep learning works. But before that, we're going to get like a survey of, where everybody is with deep learning, just so we can get an idea and kind of tailor the deep learning intro to the audience.
Mm-hmm. Okay, so we have a couple of questions to sort of gauge your understanding. Raise your hand if you know what a fully connected layer is. Okay, convolutional layer. Okay, who knows what a gradient is?
Great.
Okay, and who knows how to use gradients to update the parameters in a neural network?
Okay. I guess we can more or less speed through. Please stop at any time when you don't understand anything.
Yeah.
We'll try to wait for questions as well.
Okay. So with that, disclaimer, this is not at all a full overview of deep learning. This is sort of just getting your feet wet so you know the basics enough to sort of understand what GANs are doing. But if you do want to learn more, these are some of our favorite resources. We have our own machine learning crash course. Part 3 is about neural networks, right?
Yeah.
Stanford has a good course, 231N, on convnets, which we'll talk about later. The Deep Learning textbook by Ian Goodfellow is a really, really good resource for anyone trying to get into deep learning and sort of wants a foundation. And then Coursera has an intro to deep learning class as well.
All of these are free, so that's a good point there.
Okay, so let's start with sort of the fundamental unit of deep learning, and that is the neuron, and you compose these into neural networks. Basically, how a neuron works is it takes some scalar inputs. You can see we call them input 1 and input 2. You multiply them by some scalar weights, weight 1 and weight 2. You add a bias, which is another scalar. You pass through an activation function, and that's your output. Now, this sort of seems like a bunch of jumbled math, but basically, if you just write it out on the left as each weight times each input plus a bias, and then the sigma is activation function, which is a nonlinearity. You sort of get the mathematical notation for that. For those of you who are familiar with linear algebra, this is actually a matrix multiply plus a vector add, and then you have an activation function. And basically what you can do with these neurons is right now they're just sort of jumbles of math, but you can arrange them into layers. And if you connect these layers in a way, these are called networks. Basically how it works is you have an input layer at the very beginning. This is where you input whatever data you want to learn on. And then you input this into the next layer of neurons. which do the math I just described. And then the output of those neurons becomes the input of the next network. And you sort of chain these functions together to create a sort of complex model of behavior. And if you look at below, you can see that it's basically a nesting of a bunch of matrix multiplies, a bias add, and then a nonlinearity. And that's basically the mathematical formulation of neural networks, and that's typically how they're structured.
Yeah, so neural networks learn by taking in a data set and then trying to adjust the guesses made by that neural network using a loss function. So the data set is typically composed of pairs of features and labels. So features may be like images of cats and dogs, and the labels might be the classification, whether it's a cat or a dog. Our loss function would then measure whether or not our guess made by our neural network was correct or not. So let's say the network guesses that an image of a cat is in fact a cat, then this example loss function would assign a 0, because our loss function should be greater whenever we incorrectly predict something and smaller when we correctly predict something. Now this is a very simplistic loss function. Some more complicated loss functions that are typically used in practice are the MSE, mean squared error. Basically, that's just the difference between the output of the output label, and then the true label. That's typically used for kind of regression tasks where you have like a real valued output. We additionally have like a cross-entropy loss, which is typically used for categorical stuff. So the MSE is going to be a little bit more important for these kind of tasks, these kind of generative tasks, because it's a regression task. However, the GAN formulation actually allows us to avoid these loss functions entirely. Oh, okay. So neural networks learn by basically taking some details about the input and then passing that information back backwards through the network to adjust the weights. So we adjust the weights by this notion of gradient descent. So we calculate a gradient with respect to the loss function. Basically, the difference, or the amount we need to change our weights of this first output layer, basically just the layer that's closest to the output. And we know how much we need to change those weights so that we improve the loss function, basically decrease the value of the loss function. And then decreasing this loss function is kind of like finding the bottom of a hill, basically. So the idea is that you're like a ball rolling down this hill, and the idea is you're supposed to try to find the very, very bottom. And that is going to be your minimum. So it's kind of just like a typical minimum optimization problem. From there, what we can do is, once we've calculated the gradient at this layer right here, we can actually go back and we can pass this gradient through a method called backpropagation, which basically takes a function of the gradient of this layer and then the weights here, and then sets up a gradient for these weights right here. And then you can pass that further, get a gradient for these weights, and so on. And then you can just descend this gradient for the loss function, with respect to the loss function at every single weight. Yeah?
How do you find a gradient at each layer? Is it like the partial differentiation?
Yeah, so you basically use like chain rule to actually figure it out. So you've already partial differentiated out here at the loss function area, and so then you can just like use chain rule to get it back. Yeah. Cool.
So a good question to ask is sort of what these layers actually learn to do, like what operations they perform on the inputs to get the outputs. And as it turns out, especially for image-based tasks, there's a pretty good way of thinking about that, and that's sort of like a hierarchy of abstraction. For example, in the first layer here, in this sort of like imaginary neural network to guess whether it's a dog or not, perhaps it would take in pixels of an image and learn very low-level features, like are there edges here, are there ovals here, are there circles here? And from those sort of higher-level representations, which are more informative than, say, raw pixels, you can get even more detailed in the higher-level features. And by features, I mean basically just like attributes about the input data. For example, you could learn whether there's fur, whether there's eyes in the given image. And from that, if you like abstract that enough, you have enough data to basically guess whether it's like, say, a dog or not. And this sort of way of thinking about networks as hierarchical abstraction is very useful to understanding how like they learn and work. And a recap. Neural nets are composed of layers of matrix multiplies with a nonlinearity. We need data and a loss function to train a neural network, hopefully a loss function that's informative and relevant to our task, and a good data set that allows us to learn the correct function. Neural nets learn by calculating the gradient to the loss function, then descend the gradient to a local minimum. And neural nets build abstractions on top of abstractions while learning to make complex decisions. What I sort of described here, what we described here is what's called a fully connected network, where basically every neuron is like sort of not tied to any of the other neurons, and every neuron goes straight into the next layer.
Yeah, so this is a fully connected.
Yeah, so as you can see, all pixel inputs are connected to all of the next layer and so on and so forth. However, that's actually not the best way that we could learn based on images. In particular, convolutional neural networks use a different set of operations to get your features, and they work much, much, much better on basically any image-related task and a few other tasks as well. And basically how they work is instead of these matrix multiplies, we have what are called convolutions. And the concept of a convolution isn't too bad. Basically, you have a weight filter, which you see on the left, which is sort of a set of numbers in like a square matrix, perhaps. And then you slide this weight filter across an image, and then you basically do a dot product for the pixels in the weight filter, add that up, and then you have a feature. And the reason this is useful is you have the same weight filter across the entire image. So at the end, say if this weight filter may detect an edge or something, you'll have a set of features that correspond to where the edges are in the image. And this is a much better way to extract information from an image. And here's another representation of how they sort of work. You can see it sort of slides across the image to get more information. You guys have any questions? Yes?
So how do you decide the weights of the weight filter and how it's arranged?
How it's arranged, you sort of just put in, it's part of your architecture, you sort of decide that and you sort of guess. Typically it's like 3 by 3 or 5 by 5, and then the way you slide it across, there are many ways to do it, but you might do it by 1s or by 2s. And then the actual numbers in the weight filter, those are the learned weights. So that's what you're actually learning when you're computing these gradients and you're updating your network. You're learning these filters. Yep.
So you're mentioning that this is 3 by 3 or 5 by 5, so this is mainly for detecting edges, I'm assuming?
You can use it for detecting edges, and in fact, in the lower layers of the network, that's what it does. But again, we mentioned that if you can build up abstractions. This allows you to build up abstractions. So I guess you can use this like edge detection at the earlier layers to build up other information. I mean, convolutions are not just isolated to edge detection, though. You can do like blurring and stuff. So there's a few operations that it can actually do. Yeah,
and at the very high levels, if you sort of like pick apart these networks, it can learn some like really complex features. Like it can learn like where faces are, or where like wheels and spirals are in an image. So like it's not just for edge detection, but there are a lot of useful reasons for this.
There's in fact actually 2 slides that we removed from this that are still apparent in the slideshow. If you go look on what we shared, you can go check those out.
And it sort of explains this concept a little bit more. We felt it wasn't super relevant for GANs. And do you want to talk about convolutional layers?
Yeah, so the basic concept of convolutional layers is that you not only have like a 2D matrix, but you actually have a 3D like volume basically that you're dealing with whenever you're running you're passing data through the convolutional layer. So the input is actually a 3D volume, especially if it's an image. The image has 3 color channels, RGB, and so it has a depth of 3. And then it also has height and width as its other dimensions of that volume. And so a convolutional filter will typically actually go through the entire depth, at least in kind of traditional image convolutional neural networks. It'll go through the entire depth of the input of that convolutional layer. And then each filter will produce a filter slice, I guess, in the output volume. So that means that our output volume will have some dimensions for its height and width. If you set stride equals 1 and have no padding, then it'll be equal to the same exact size in height and width. But then the depth will be equal to the number of filters you choose.
So upsampling, this will become a little bit more clear when we talk about GANs, but what basically happens as far as what we've talked about so far is you go from an image to like basically smaller and smaller like I don't know, summaries or features of that image, but that basically reduces the dimensionality of what you're looking at as you go throughout the network. However, when we're doing the generative part of adversarial networks, we go from a random sample of noise to an image. So that goes from a low dimensionality to a high dimensionality. So the question goes is like sort of how do you create this increase in dimensionality? So Deconv is called deconvolution. It's basically the inverse of convolution. It basically does the reverse operation. But technically, it's called fractionally strided convolutions, which is a bit of a mouthful. But basically, if you can see from this image that you add padding in between the pixels, and then you convolve, and then you have an increase in dimensionality. So technically, it's still convolution, but it increases your dimensionality. However, in practice, this doesn't really work very well for a lot of tasks. I mean, it works fairly well, but you notice there are what are called checkerboard artifacts. And basically, if you look close into the image, there are a bunch of like really weird checker artifacts that look like really aesthetically appealing. And that's because of the intrinsic sort of nature if you like stack a bunch of these together. A better option, which is, no, we're not going to talk about later, but basically you resize the image using like nearest neighbor interpolation and then convolve classically over it. Do you guys have any questions?
Yeah. Would deconvolution like losslessly recover the original that you convoluted?
Wait.
What do you mean by that?
No,
like,
probably.
let's say like you have like a 100 by 100 and you like convolute like by like 3 by 3 into like 98 to 98. Would you, if you go back with deconvolution, would you get back the original 100 by 100?
No,
Or
no,
you
you're
lose
losing
some
information.
Yeah, when you sum up, you lose information.
Okay.
So,
Mhm.
yeah.
Any other questions?
Okay. Now we get to the meat. So yeah, I'm going to introduce the basic algorithm behind GANs, at least the intuition behind it. And I don't think it's terribly crazy to understand. You can kind of formulate it like a two-player game. In our case, we're going to have one as like, kind of like an art critic, somebody who's like supposed to be an expert in determining whether art is real or not. So he has like a cop hat because he's kind of like a cop. Well, we have another player who's kind of like an art forger. So he's trying to make a lot of money, but he's not a famous artist, but he knows how to copy famous artists' artworks, or at least he thinks he does. So he starts out and he creates this picture of a cat, and he's like, okay, it's time to make a lot of money. And so he gives this to the art inspector, and he's like, okay, it's time to give me my money. Look at this original piece of artwork. And the art inspector is no dummy. He sees this and he's like, okay. Maybe I'm just starting out, but I know for sure this is not a good picture of a cat. It's fake. And so the art forger is like, oh damn, I didn't get my money this day. So he goes back and he starts thinking. He's like, how do I become a better art forger? How do I start making my millions on the black market? And so he grows, he evolves. He learns how to create much better artwork, and he produces this magnificent piece, also a drawing of a cat. And then the art inspector is just amazed. He loves it. He thinks it's the best piece of art he's ever seen. And he thinks it's an absolute true piece of art, like that is worthy of putting into any gallery. So he calls it real. However, he sells it to an art gallery, and then quickly that art gallery is shamed because they realize that it is in fact a fake. And so he must go back and he must think about what he did wrong. He must look at this image and he must think like, what in this image gives it away as a fake. And he grows, he figures it out. And now he can clearly call it a fake. So you can imagine that this game kind of goes on. The generator gets the forger gets a lot better. He gets better at creating art that fools the discriminator. The art inspector. And the art inspector subsequently also gets much better at determining that the art is fake or not. Eventually, they become just absolutely super evolved forgers and art inspectors. So the forger is creating beautiful pictures of cats, while the inspector is really great at understanding whether or not the forger is making realistic-looking images. And eventually, they actually reach an equilibrium where neither of them really are good or can distinguish each other's or can fool each other at this point. So, the generator has a really hard time at fooling the discriminator, and at that point, they reach kind of equilibrium. Do you have a question?
So how do you essentially prevent the adversarial networks from reaching a deadlock?
We'll talk about that later.
Yeah. That's a really open problem, I'd say, and you kind of just hope that it works for the most part.
That's not a joke.
So you may have heard me kind of lapse into talking about these as generators and discriminators, and that's the actual technical term. So the art forger in kind of the neural network case and the generative adversarial network case is the generator, and then the art inspector is the discriminator. So the generator tries to create some data that looks like real data to the discriminator, and the discriminator's job is to figure out whether that art is real or fake. They both start out pretty bad. They're like randomly initialized. And then as they train against each other, and eventually they can produce actually pretty good results like the ones you saw at the very beginning. So this is kind of like how the neural network would look like, or the neural networks would look like. First, you have a random noise on the very left here. So that's typically like a 100-dimensional vector that's sampled from the normal distribution. Basically, you can just think of it as random information. And then that's passed into a generator. We upsize it a few times, and then we get a final like input image that looks like an image, hopefully at the end. And the discriminator is then fed a data set that is filled with both real images, images from our training set, and images from that are generated by the generator. So each of these images has a label, and the discriminator is tasked with labeling whether the image that it's seeing at a current moment is fake or real. So not too crazy. That's the basic algorithm. So, I forgot to fix this. Okay. Yeah, okay. So there's this, the loss formalization, that actually first equation is wrong, I'm sorry. This is the second time I've left this up here, but I apologize. So we try to maximize D with respect to actually the equation on the bottom, the equation right here. So the idea is you try to maximize the probability that the discriminator, or the confidence that the discriminator gives on data that's pulled from the true data distribution, basically the real data distribution. And then you want to subsequently minimize the confidence in the discriminator's classification, or sorry, minimize the, whatever, just say like maximize the chance that the discriminator correctly classifies the generated output from the generator, so the fake images. But on the other side, the generator's task is to trick the discriminator, so it tries to minimize the same equation, I guess, section of the equation that the discriminator tries to maximize. Yeah?
Explain what Z and X is?
Yeah, so Z is the random data distribution. So basically that's just the all the possible random vectors we can input into the generator. You said X?
Yeah.
So X is a sample from the true data distribution. So that's basically just all the like real images that we have, all the real digits or real artwork or whatever. So so PZ is like the data distribution, and then Z is like the sample from that. Yeah.
So is the generator always taking in a random vector?
Always, yeah.
Okay.
Well, there's actually some modifications where you can add like extra information as well, but in kind of the classic GAN, it's just a random vector. Yeah.
So the generator basically takes a bunch of noise and somehow forms a face out of it?
Yeah, yeah. What it does is it creates like neighborhoods of these noise vectors. So it'll be like, okay, noise vectors that are noise vectors that are near each other should have like similar faces. Mm-hmm. That's how you're able to get that like. So at the beginning, that like video that we showed at the very beginning, that's called like interpolate. That's just interpolation in the Z space basically. So you interpolate these vectors, and it was able to create these kind of like smooth transitions between faces. So, yeah. Cool. So we have a quick demo for you. Hopefully it should work. Oh, yes it does. Okay, cool. So this is in the repo that we mentioned at the very beginning. Basically, I'll just kind of run through this talk about like the details that I brought up during the beginning of this presentation, and hopefully, I invite a lot of questions to this because this is kind of like the meat, I guess, of this slideshow. So I set a batch size to 128. Our learning rate is actually really low compared to other network models.
Especially for this size.
Yeah. So additionally, we have a parameter that controls the optimizer as well, known as the beta. Basically, this is related to like momentum and all that stuff with respect to stochastic gradient descent. You should look up. There's a few good videos online, especially from this YouTuber called Sirajology, and he talks about optimizers and how different parameters and optimizers work. It's a really interesting talk, and I would recommend if you're interested in learning more about optimizers. But that's not the point of this. So our generator model, as I mentioned before, takes in an input of 100-dimensional random noise, basically. So that's what this comes in, and then we take in units. We have a 1,000-dimensional layer after that, after the input. As a note, this is code that I grabbed from the internet today. So typically, when you have an activation function, more recently in deep learning, you'll use something like a ReLU. In this case, whoever wrote this used a tanh. I didn't have a chance to play around with the parameters and actually get ReLU to work, because I did try exchanging tanh for ReLU, and it just didn't train as well. So you should try that out on your own, because this takes maybe like 20 minutes to train on a laptop, which is really nice compared to like typically requiring, I don't know, several days on a GPU. So this is awesome. Yeah, so after you have your activation, we have another dense layer, batch normalization, activation, and then we reshape it so that we can start doing some upsampling stuff. So I believe the upsampling here is probably just like the decom stuff, that we mentioned at the beginning. And then we have our activation, another upsampling, and then another convolution. Oh, you know what? No, this is resize conv.
Very sure.
Yeah, it's upsampling. Because upsampling.
Oh, upsampling.
Yeah, so sorry about that. Yeah,
this actually is resize.
So this is resize. Resizing, all it does is it resizes an image to be bigger, or I guess in this case like a volume. It creates it a lot bigger using nearest neighbors interpolation. And then from there you can just run a convolution on that. And that's effectively very similar to the fractionally strided convolution that we talked about earlier. Yeah.
Are these generator and upsampling 2D, are they all from TensorFlow?
This is all Keras. I don't know how to pronounce it. I've heard it pronounced many different ways. But yeah, so it's all Keras. You can see right here. It's actually a library within TensorFlow at this point. So it's pretty easy to find. It's a really nice high-level version of, or high-level, I guess, wrapper on top of TensorFlow. Would recommend trying it out. Yeah, so we have the generator here, sampling convs and so on. Now we have the discriminator. It's kind of a typical, just like convolutional neural network. We have a conv2D, activation, max pooling, conv2D, activation, max pooling, flattens out into a dense layer, so like fully connected layer, and then finally gets into a single output, a single dimensional output, which basically is a 0 if it's real and a 1 if it's fake, if the image is fake. One if image is real, and 0 if image is fake. Sorry if I got that confused. Okay, let me make sure I run these. This right here, just make sure that the generator is in the discriminator, or sorry, discriminator is in the generator. This is just good for like setting up training. Don't worry about this line. This just combines stuff for saving samples. This saves samples. And this is the training code right here. So first we load in the MNIST data. We normalize the data using just like taking out the mean and then dividing by the mean so that it's just like between, I think, 1 and 0, something like that. And then we set up our model right here. Oh, whoa, sorry about that. Oh, no. Okay. Yeah, so we set up our model right here. We set up our discriminator, we set up our generator, pass in the discriminator into the generator, and then we set up our optimizers. We use Atom. Atom's just like the state of the art of neural networks, basically, in terms of optimizers. Generally, if you're looking for an optimizer, you should just use Atom. I've rarely seen a good reason to use anything else. Then we compile these all together, and finally get into the actual training code. So you can see here we sample our noise, and it's 100-dimensional. So this is going to be the vectors we pull out for the generator. And then subsequently, we also have an image batch, which is of the same size. This is just the data we'll pass into the discriminator. And we generate the images. Then we concatenate these images that we grow out from the data set, and then plus the generated images. Then we create labels for these. It's really simple. Make sure that the real images have 1, a label of 1, and then make sure that the fake images have a label of 0. And then we calculate the loss on that batch, and then use that to update the discriminator. Yeah, so I think these lines right here, these .train on batch are what actually update the specific models. Cool. And so now we can watch it train. So I think I'm using a GPU right now. So it's pretty fast. And we can actually probably leave it running for like 30 seconds and it actually will produce these results. I also have one saved on my computer that's pretty fast. That's pretty good already. But as a note, it should only take about 3 epochs. I think we have it run for 100 epochs here. But if you run it for, let's see, it'll finish at an epoch right now. Yeah, so right here it's finished epoch. It's finished epoch 1 or epoch 0, and so it'll already probably be pretty good. So I'm going to stop that for now because I don't want to sit and watch it. You totally can on your own. So I'll run this code that displays the image. This generate, it's basically the same thing as the generate code that was inside of the training code. It's just a little bit more abstracted so that you can do nice training stuff. And now we can display, what is this? Batch normalized 2, okay. Well, act like that worked. And then, so we already have like a pre-trained model, and you can see that it produces pretty good results already. Like very clear that there's like 1s and 0s and stuff like that. This 3 is pretty good, but then you see there's a few errors still. Like, what is this character right here? Like, I don't know, it could be like a 9 or a 3. Also, this, what is this? But it's still pretty good. This took me maybe like a minute to run on a GPU, which is really nice, and then would probably take you maybe 20 minutes to run on like just a standard laptop, which is not bad either, especially when you're thinking in deep learning scale. Does anybody have any questions? Yeah.
So in the training section, you train once on the discriminator, and then you train on like D on G.
Yeah.
So is that like? Can you explain why? Or are we not training on just the generator, or?
So the D on G takes in the information from the discriminator. Basically, just says the discriminator gives it a loss. I think. Yeah, I think it gives it a loss at that point, and so that you can use that loss. So the discriminator acts like basically a loss function to the generator, and so the discriminator D on G is basically just the generator with the discriminator as the loss function at that point. So, yeah.
Does Keras basically handle all the like generator adversarial parts?
The D on G stuff, that more or less handles it. But yeah, I'd say Keras, I guess, it doesn't really think about the adversarial stuff exactly. It just so happens to be that the way we set up the network already takes care of that. Yeah, I guess it's like we've coded in the stuff so it doesn't have to worry about like Keras doesn't really care about whether it's adversarial or not. It could be like completely different graph or a completely different network or anything like that. Nick?
It was obviously a very small sample, but I noticed a lot of 1s. Does the generator tend to overfit towards like simple representations?
Maybe not simple representations, but it does happen to overfit to like certain like outputs.
We'll talk about it later.
Yeah,
Okay.
This is known as mode collapse. We have a section on it.
Okay.
It's a very common problem with generators. Yeah. Cool. I guess we'll get back to the slideshow.
Okay, so GANs have a lot of cool properties that we can sort of explore. We've touched on a few of them already. The first one we have mentioned a few times. It's called image interpolation. Basically, how it works is you sample the z. The z is the random noise, and you sample another z, and basically you compute a linear interpolation between those two vectors, and you pass those all into the generator, and you can basically create a smooth transition between two arbitrary samples. In this case, they're faces. And what's interesting is that at every point during the transition, you still get a face out. So you can sort of mesh and mold arbitrary faces and have one transform to other, and that's the video we showed you at the very beginning.
I'd also like to note that like you can get a lot of variation inside of these images, and it'll find intermediates between them. So for example, you can see I think the bottom one's probably the most striking. You can go from changing like skin tone and gender entirely, and it produces images in the center that are convincingly still people, even though that they may be like more like the ones in the very middle may be a little bit more androgynous than others. Yeah.
All these faces fake or real?
All the ones except for the input A and input B are fake. Yeah. Yeah.
And so do the real, like, do input A and input B not exist, like as vectors inside?
So
it kind of looks like a little off at the edges.
Yeah, they don't exactly exist in there. What you can do is you can take the generator and you can back propagate the image through the generator. Yeah, and you actually have to use a method of like a separate method of optimization because like you can't, a neural network doesn't work where you can just like reverse the network and just get like the right representation out.
It's one way.
Yeah, you have to do like an optimization to get it to like a proper Z.
And is that like what with the video we showed at the beginning, or were those? Did that start with a real input, or were those all?
Those were all.
Those
just.
Are all fake.
Yeah. They just sampled random noise for every single one, and then they just interpolated between those. So.
Any other questions? Okay, another thing you can do that's pretty cool when you have these sort of compact continuous representations of these images is you can do input space arithmetic.
That's a really slow animation.
I'll just put it all up here. So you can take the Z vector, the random noise of a smiling woman, and you can straight up just subtract the vector of a neutral woman, just like literally just subtract it, add a neutral man, and somehow by the hand of God you get a smiling man. And you can see in the middle that sort of like maybe the neutrals cancel out and you get a man. And basically the way this works is that similar vectors have similar outputs in the image space. And if you're wondering why these results aren't as like high-res and beautiful as the ones we've seen before, is that like the previous ones are the most recent research. And this is from DC GAN. We'll talk about it a few times again. This is sort of like the classic baseline GAN model that you can find online that works really well for a lot of data sets. And it's a great starting point for like any...
Oh, for a lot of image
For
sets.
a lot of image GAN stuff. Yep.
And so if you did the input space arithmetic on like the month-old research, it would look just as good as like the interpolation?
Almost certainly.
Maybe,
probably.
I don't know.
Well,
that's
it would look a lot better, right?
I think it would look a lot better. I wonder if it would still work. I haven't tested it out
I
myself.
suspect so.
Yeah.
It's hard to say. Yep.
Yeah.
So is this similar to how, like, for example, like word-to-vec generates words, like word relationships between words using vectors?
It's the same kind of arithmetic that they demonstrate in Word2Vec. Like you can do in Word2Vec you can do like women or like king minus woman equals queen or something like that. It's the same kind of idea. Sorry, the question back there.
Yeah, how would you encapsulate the differences with facial features? I mean, there are vectors, they can be represented, the pictures themselves can be represented as vectors as well, but how do you encapsulate the features themselves?
It's learned. So this person just put in the data set of images and just fed the random noise, and it just so happened to learn this representation. So it was like...
Just how it happens.
Yeah.
It's kind of black magic.
Yes. Well, because the generated output is not, like, you're not saying output a specific image for each noise, right? Eventually, you're just saying produce a real image. So it could produce anything, and as a result, it actually creates this like smooth manifold of the input. Yeah.
So for like, so if you adjust the weight of smiling women, can you turn it into like a grinning man or something?
I don't know about the weights exactly.
Perhaps there is like one part of the vector that's responsible for sort of like the smiling or perhaps like the overall emotional tone of the image. It seems unlikely, but there are some ways that you can sort of trick that into happening. It's called InfoGAN. We don't really talk about it here, but you can look it up after if you want to do that.
Also, with respect to that, you're dealing with like a 100-dimensional vector, and it's possible that it could be that every single dimension actually is like responsible for smiling. So that's really hard to like separate that out from just this formulation. But the InfoGAN one.
The InfoGAN can do that?
Yeah.
Okay.
Yeah, what was your question?
Are GANs used for like text generation too?
I've heard a little bit about that. I'm not the best person to ask though. There's some research out there though. I think you can find some information.
Typically, you don't use it for discrete outputs though.
Yeah, it's not very.
It doesn't work very well.
Yeah.
Another thing you can do is called conditional GAN. And the idea here is pretty simple, is you add extra info to the generator's input in addition to the Z vector. There are a number of things you can choose. The most obvious one is class labels. Like if you're training on the MNIST, like the digits, in addition to just adding the random noise, you can also add the class label. And that means that like if you say you wanted 1, it'll output a 1, and you can do this during training, and it'll learn that mapping. And typically, if you actually do this for basically any data set, if you have those labels, it greatly improves performance. So like if you want an easy way to like improve the power of your GAN, you can do that. There's a lot of other fancy stuff you can do with conditional GANs. You can do text embeddings, like you were talking about earlier. This is from what's called StatGAN. We talked about it a little bit later. You basically stack GANs on top of each other, but what they also did is they learned the captions of the images, right, from a data set, and then mapped those to the images.
I guess they had the captions, they embedded them into something like Word2Vec, and then they use that as the conditioning.
And basically what you can do is you can type in a description of, say, in this case, a bird. This vibrant red bird has a pointed black beak, and it does it. And that's pretty cool, because like, how else are you going to convert straight text into images? I don't know. And then there are a few other things to do. You can do like sketches, and we'll talk about that in a little bit.
Yeah.
Do you have a question?
So that type of generation is contingent upon the pre-labeled like training set?
For the class labels, you do have to have the labels during training to effectively basically learn a mapping from the labels to the outputs. Okay. You want to do pix-to-pix?
Yeah. So this is a really cool result that I think has led to a lot of other cool like papers and kind of experiments that people have done as well. It's called pix-to-pix. It actually came from Berkeley, from a postdoc who just left. His name was Phillip. He worked in Efros's lab. What it was able to do is that it was able to take like paired images that were like, one of them is like labeled details of the other image, and then it was able to create a mapping between them. So for example, they have like aerial images of from Google Maps, and they also have the same like kind of street images, the ones you'd see if you're looking at like the GPS or something like that. So what they were able to do is they're able to take input of these like other aerial maps, and they could just easily create these like Google Map drawings, basically. Additionally, I think another cool one is the edges to photo. They're able to take like a bunch of data sets where they grabbed the edges from the photos, and so it looks like a sketch. And they're able to basically sketch out a new example from this data set. We actually have a demo that I'd like to show. I think you'll like. Yeah. So as you can see here, they have some sketches right here. And you can go in and you can just sketch these yourself. So this is something that I did earlier. I went in and it first gave me a picture of a cat, and it produced like a normal looking cat. So I wanted to give it a third eye, so I just drew like a circle on top. And so yeah, you can check this out. It's at affinelayer.com/pixrv.
Draw something.
Draw something? Draw like a smiley face. Wait, let me get the eyes.
Let's get some.
Yeah.
This is gonna look great. It's probably just gonna be fur. I don't know.
Yeah, it could just be fur. You can see there's like a nose right here. Already. There's like one eye that showed up.
Or do you like start over?
Start what?
Like clear it and then
Do like a random one. Oh, this one's.
Needs one.
No, let's just do another one. Yeah, there. Has
Draw
one
some
eye.
English letters.
What?
Draw some Latin letters, see what you get.
I wish I had a stylus.
Go on, do.
Oh, I know.
You should have a toaster cap too.
Yeah, well, we have some good images from like good artists. Yeah.
It's really good stuff.
Oh, it's gonna look horrific.
Oh. So yeah, clearly.
Add some of the H in the I, you know.
Yeah. So clearly, it doesn't expect sketches to be kind of like discontinuous. At least in this case, if we trained it on something that maybe had discontinuous pieces, it would learn it. But in this case, it tries to maintain global coherence because it's like, oh, it doesn't really make sense that there's sketches out here.
You do your best, yeah.
Yeah. What was your question?
So are these inputs like replacements for what would have been the noise?
They actually keep the noise in there too, I think.
Okay.
So they just basically take this extra input and then they concatenate it with the noise.
Okay.
Yeah. Yeah.
So this thing could only do cats, right?
Well, I mean, you just train it for other stuff too. You can train it for handbags. I don't know. You can add another thing. I don't know if that'll work. I think that'll actually. Yeah, that's what I thought it was gonna do.
It's not in the handbag space.
Yeah, I'm also not good at drawing handbags. Hey, look, I got
Hey,
it.
not
Yeah. So yeah, you usually have to specialize it, and that produces the best results. And that's something we kind of touch on later. Okay. Any other questions about that? Yeah.
Can you also condition on text descriptions?
Exactly. Yeah.
Yeah, just say
That-
have
that-
a NLP process.
That's in fact the example we gave.
That's a
before.
stack GAN.
Yeah, right here. Yeah, a bunch of GAN papers have done that.
Conditionals.
And,
They condition on the text, yeah.
and then could you also combine like text and sketch?
You could
and
do
then
whatever,
bind
as long as you have the data, you totally
Yeah,
go
if
for
you
it.
have the data.
Exactly.
Yeah. And I guess that is the real limiting factor for a lot of these. Like, just data is like expensive to get or doesn't exist. Okay. Yeah, we'll continue. So here's some really cool results that people have done with that cat drawing. Yeah. So you see like some toaster cat and then PlayStation cats. Okay. So GANs are really cool, but they also have a lot of problems. Yeah.
Okay. And they have a lot of problems. So the first problem is measuring quality of your samples is difficult. Like when you're trying to classify like images into dogs or cats or whatever, it's pretty easy to tell how well you're doing. It's your accuracy, it's your loss. But like with GANs, there's no like one loss that describes how well your sample quality is. And to illustrate this, like we can ask like which one of these is better. Like if you think the one on the left is better, raise your hand. All right. If you think the one on the right is better, raise your hand. That's what I thought. Well, it's pretty obvious to tell because the left is the real image and the right one is generated. And like even here, it's hard to say like mathematically what that even means. Like intuitively we can see it, but it gets even worse because these are two generated images. Which one is better? If you think it's the one on the left, raise your hand. One on the right? Yeah, it's really hard to tell because they're both pretty bad actually. They actually look horrifying. But in general, during training, when you have these like bad images, it's very, very difficult to tell. Like if your training is improving, if your sample quality is getting better, you just sort of have to look and guess. There have been a few research advancements in this sort of area.
Oh wait, I'd like to note one more thing. It's also really hard to tell like which one is closer to an actual dog.
Mm-hmm.
Yeah. So.
Especially trying to do that quantitatively sounds like a difficult thing. Attempts to measure quality. The first one's an inception score. And sort of the classic solution in deep learning is throw another neural network at it. And what this does is it uses a neural network to measure the quality of a set of outputs. And sort of how it works is if you're trying to train on a data set they already know the labels for, and then you train a neural network on those labels, like classifying an image. When you run that network on your generated images, you want two properties. First of all, for each individual image, you want the output of that network's probability for a certain class to be very high. What I mean by that is if you give it an image of a dog and it predicts that it's a dog, you want it to have very, very high confidence that it's a dog. It means your image is good, right? Because if it has like maybe 60% confidence it's a dog, maybe it's not a good image, it's not indicative that it's a dog, whatnot. And also across a set of sample images, you want a lot of variation. And what that means is you want dogs, cats, bicycles, whatever you are trying to generate instead of just like dogs all the time. And you can basically mathematically formalize that, and that's called an inception score. Another approach is human trials. Those who don't know, Amazon Mechanical Turk is a way to pay people to do extremely, extremely menial tasks.
Or
basically,
get paid to do menial tasks.
Huh?
Or get paid to do menial
or get paid to do
Whatever
menial
you want.
whatever floats your boat, honestly. But what you do there is basically like either ask them to like measure how good each output is, or you can ask them to be the discriminator, and then you like can measure from there like how good your network is. But that's like intractable and expensive. The most recent advancement is called MSSSIM, Multi-Scale Structural Similarity, which is a mouthful, and it comes from that paper we've been referencing a lot, Progressive Growing. That's like a few months ago, or 1 month ago, whatever it is. And I don't know the exact details of how it works, but it works pretty well, and basically it gets image information from various scales of the image. Do you know anything more about that?
Yeah, so it takes like it takes samples from the Laplacian pyramid representation of an image. Basically, it gets what? The Laplacian pyramid of an image. It's a common image processing technique, and then it compares these samples to randomly sampled samples from the data set as well, at these different scales. And then you can kind of create like statistical measures of what details should be in each part of the image.
And that's pretty well. Another problem we touched upon earlier is called mode collapse. This is extremely, extremely common, and it's sort of easy to diagnose, but it's difficult to fix. When you have a sample of images from a GAN, many inputs map to the exact same output. As you can see here, this is something that we did earlier, and we had this problem. Yeah, no, this is straight up us. But as you can see, a lot of the images look virtually identical, and that's because they are. And if you think about it a little bit, it becomes kind of clear why this happens. Like, there's no reason for the generator to ever like really try to create a lot of varied outputs. There's no like incentive for it to do that. Basically, like if you're training on MNIST digits, it'd be very easy for the generator to just like output very clean, beautiful ones all the time, and it will always fool the discriminator, and it doesn't have to do anything else. I guess it's lazy in that way. And there are a few ways to address mode collapse, but we'll go. It's sort of complicated, and we'll go over it later. Does anyone have any questions?
What image was trying to be generated in this case?
So that's a bit of a more complicated question. This is trained on a data set of art, but we're not directly trying to create the art from the data set. We'll talk about it a bit later. We're trying to create the creative art, and basically, we'll talk about it later.
Yeah, we'll come back.
It'll become clearer. But basically, this problem happens with regular GANs too, but I think it might be worse for GANs. It's hard to say. Another issue we touched upon a little bit earlier, poor output structure. It's very difficult for these networks to capture the structural properties of the images for a lot of data sets. On the right, these are all supposed to be dogs. None of them look like dogs. And I guess it's hard for the discriminator to say like a dog has 2 eyes, 2 ears, 1 face. It just says like dogs have ears, eyes, faces, and furs.
You should also consider the fact that the discriminator learns from the generator as well, like what the good details are. So, given that information, I guess that's never mind. That's not fully formed.
Yeah. Well, also if you think about the way that convolution works, there's really no reason for. There's not an easy way to describe exactly like how many features you want. I don't know.
Yeah, how many like features like eyes
should be there,
or legs, or
it's only like if they're there or not. Yeah, or whatever. Often this is not much of a problem with data sets with many similar images. Like there's a data set of like very well cropped, the same size birds, and if you run into this doesn't really happen because it's not really exposed to a lot of variation.
Also, I think the big reason why there may be a lot of legs or something like that, or a lot of different features, is that a lot of these images end up being composed of many different animals. So you may have like an image with a few cows or a few dogs or something like that. And so when the discriminator sees pictures of dogs and may see all these legs and be like, okay, that's okay.
Yeah, that's totally fine. Yeah. But it's not fine. It's not fine at all. Another issue is that training just straight up fails often. This is really difficult to control, difficult to understand, and pretty much one of the biggest pains of GANs. These are, I don't know if you guys know what TensorBoard is, but basically it's a visualization tool for TensorFlow. It's really, really useful if you want to monitor your losses and stuff. And on the right is some losses from an experiment I ran. There are so many problems with it, it's kind of hard to know where to start. Right here, this is DLoss fake. This is how well the discriminator predicts whether a fake image is fake or not. Basically, you want this to be sort of oscillating because you don't want it to be too good, otherwise the generator's failed.
You can show the next time.
Yeah, DLoss fake right here should just be oscillating like not too close to 0. Here, I don't know if you can see the scale of this, but this is basically 0. It started immediately at 0, then just oscillates wildly and just stays at 0. So the discriminator learned extremely quickly, almost immediately. And then DLoss real was basically oscillating, then went down straight to 0 and just stayed there. We also had this network try to classify images into different styles, and I don't know why, it just exploded.
It just became really bad at classifying.
It just got worse and worse and worse and worse. And then we stopped the experiment. But I accidentally let this run once and it went to like several thousand, so.
Was this MNIST?
Yeah, and this is on MNIST, the like really simple digits data set.
Hey, is the TensorBoard, what is the y-axis? Is it like
It's the loss. It's the value of the loss
So,
function.
the lower it gets, the better it is.
Yeah, exactly.
Yeah, well, it's a bit more complicated for GANs because you don't want any of these to go to 0 because you want the generator to constantly be fooling the discriminator.
Yeah,
But-
so when the DLoS real went to 0, that means that the discriminator can never be fooled. The
Yeah.
generator was just screwed.
Yeah, but you want this to go to 0 because you want it to learn to classify well. These are some better loss curves. They're not ideal, but they look much better. Here you can see that the DLoS class real, its classification is decreasing steadily. GLoS just isn't exploding, which is a good thing. These are both oscillating at pretty reasonable values and not going straight to 0. It's good to see a lot of oscillation between your DLoS fake and DLoS real, by the way. That's a normal thing. And your GLoS shouldn't monotonically decrease to 0. That's a sign of another problem.
Also, the shape of your GLoS will probably look different. We added another term that was related to like style ambiguity. We'll get back. This is again training of a kind of like modification of GANs, which we'll talk about later.
The general principles for like these two are basically the same.
Yeah.
And then the crux of GANs is that even on GPUs, the GANs take many days to train, unless you're dealing with very small data sets. This is even true for like 64 by 64 and 128 by 128 outputs. In our experience, this takes like at least a day on a GPU. And let alone things that look nice like 256 by 256, that took us like 4 days. And that is a lot of time and effort for one experiment. And even for high-res outputs, these are more prone to instability issues that we were just talking about. So GANs are kind of a pain to get working right. And because there are a lot of issues, there are also a lot of little improvements. There's a repo called GAN hacks. This is just a little sample from them. And there are tons of little things that you can modify to your GANs in the way that you train that can improve the way that it performs.
It's absolutely super useful if you're architecting any GAN. So.
Yeah, it's like crucial.
Yeah.
Have you guys used any of these inputs?
Yeah.
And, like,
We've used, like-
and how much like better have you had? Like how much less time did it take?
It's typically we use like half of these at least.
It's not like a time in terms
Yeah.
of like training time. It's like we actually don't fail. We don't go. The loss doesn't go to 0.
Yeah.
Yeah.
Yeah, it's less about like speed of training and more about like it doesn't fail miserably.
Yeah.
So you got like the 256 in 4 days was like with all these hacks already?
With not all of them, but a few of them. Yeah, the hacks are very important, especially like the first 2. One last improvement that I don't know if it's the last one, but that I really want to talk about is called Wasserstein GAN. I don't know how to pronounce it, or WGAN. This is a really important paper that came out I think this year from Facebook AI Research, and it modifies the loss function of GANs in such a way that 2 results happen. Basically, you get much more stable training, and you the value function actually correlates with sample quality. So this is another way to measure how good your samples are. This is the same equation as earlier, but it's a little bit more complicated. There's a bunch of fancy math behind it, but in practice, you just take away some logs and you clip the weights of the discriminator so that they don't get too big, and then you train the discriminator more. It seems like absolutely out of nowhere, and like why would this ever work? But there's a lot of like mathematical foundation behind it that like we can't really go into right now. And the more recent thing is called WGAN GP, which is basically a better form of the weight clipping, and it adds a penalty to the gradients of the discriminator to make them well behaved. And because the generator just trains on the discriminator's gradients, this makes the generator output like much better samples. And this is a little bit complicated, but you can find code for it online, and it'll basically improve your GANs.
This is pretty much the state of the art of any GAN paper that's coming out now.
Mhm.
They all
use WGAN GP.
Yeah.
Any questions?
Oh, also the GP kind of alleviates the need for the clipping in the WGAN.
It replaces the clipping, basically.
Yeah.
Cool results. This is beautiful.
Yeah. So as I mentioned before, Pix to Pix was like a pretty big paper, and this result right here is from an artist named Mario Klingemann. What he basically did is he used Pix to Pix to map images from any basically video he wanted to. He took the individual frames, and he mapped them to pictures of Françoise Hardy, which is, I think, she is a French singer who was very popular in like the 70s or 80s. Don't quote me on that. So what he did is he took a speech from Kellyanne Conway. Actually, I think I have the original one. So this alternative facts one. Oh, I wonder if I can get the sound. Hold on. You know what, I'll just try to like make it really loud. So hopefully you can hear it. Or, oh, hey, found this, sweet. Oh, that's it.
Don't be that much clearer.
Okay, I'm gonna, if you're, oh, it's not that.
Secretary in those types of terms, I think that we're going to have to rethink our relationship here. I want to have a great
Okay,
open
this is
relationship.
not the interesting part. But this is.
Chuck, I mean, if we're going to keep referring to our press secretary in those types of terms, I think that we're going to have to rethink our relationship here. I want to have a great open relationship with our press. But look what happened the day before, talking about falsehoods. We allowed the press to come into the Oval Office and witness President Trump signing executive orders. And of course, the Senate had just confirmed General Mattis and General Kelly to their 2 posts, and we allow the press in, and what happens almost immediately? A falsehood is told about removing the bust of Martin Luther King Jr. from the Oval Office. That's just flat out false. And the
it was corrected immediately.
Chuck, why?
It's a little infuriating. But besides that point, it's a little freaky. Like, you could basically train a GAN on anybody's face, take a few videos of their face speaking, and create something like this.
And in the real video, does it also zoom in on the face?
So I think this is from a data set of Francois Hardy's music videos, and so yeah, there's a lot of like close-ups and all that kind of stuff.
So, but like the zooms are only present in this alternate face. It's not present in the actual video.
No. In the actual video, it's pretty constant. It's just like Kellyanne Conway standing there. What I think is a little bit, you can kind of notice like a lot of the Kellyanne Conway's I guess general mannerisms are pretty present in the way that this alternative face works. So it's a little bit freaky, especially like the way she blinks and stuff. Yeah. So another result that actually came out from Berkeley is CycleGAN. So this is a continuation of Pix to Pix, basically pretty much the same authors, same people. And then what they were able to do is they were able to do stuff like take a bunch of images of horses and take a bunch of images of zebras, and they were able to basically make this transformation that like basically paint stripes onto horses. I mean, there's a bunch of other transformations that are really cool. The basic idea behind that is what they were able to do is they, instead of having paired images at this point, which is kind of the crux of like Pix to Pix, what they're able to do is they were able to pair sets, basically. They're saying like, this set is related to this set. So this set of horses images is related to this set of zebra images, by some respect. And then the network can automatically learn this by having 2 GANs, I think, at this point. They have one GAN that maps from like, let's say horses to zebras, and they have another GAN that maps back to horses. And then they can actually measure a loss based on the difference between the resulting horses, I guess. Between the original horse and the or other horse. And so it's like cycle consistent. So yeah, sorry, what's your question?
Is the background in the zebra video because the zebra images were trained on like a Saharian background?
Yeah, exactly. And I'm sure that the horse images were also trained on like.
That's true.
Yeah, exactly. Any other questions? A result. So this is not a perfect method, and especially if you have stuff that lies outside of the data set. So a picture that I really like that I think is really funny is this right here. So they tried to take a picture of Putin riding a horse and make it so he's riding a zebra, but it just made Putin into a zebra. So yeah, it's not a perfect thing, and especially if it has stuff outside of the data set, it's gonna make inferences that are probably incorrect.
Looks like the rocks became zebraic as well.
it's all inclusive. Yeah, I wonder if it just so happens to be that like this is a color that's very common for like
horse fur.
Yeah.
Looks like the texture too.
Yes. Okay, let's go back to this. Okay, cool. And then so this is something that we're working on. On the right, you see like an interpolation of the input space for artwork that we've trained on. Unfortunately, this GIF is not very great, but basically, we were able to train a GAN on artwork using this extra loss function that we mentioned earlier, and this allowed us to create the purpose of this extra loss function was to create like completely new styles of artwork that still remained within the data distribution. So as a side note, like we didn't do the original research. This is a paper that we were implementing because we couldn't find an implementation online, and we still think it's pretty exciting, and we think there's a lot of directions to take it. Do you want to add anything on the loss, I guess?
Basically, how it works is you have the discriminator taking in the image and then outputting whether it's real or fake. But what you can also do is tack on another part of the discriminator and basically try to classify the style of each art piece. And by style, I mean like high Renaissance, early Renaissance, Rococo, Baroque, etc. And basically,
the discriminator can tell more. That, oh, this is something else. I don't know. Instead of just real or fake.
yeah, it can basically get more information out of it. But more importantly, when you try to create these generated images, not only do you want them to be in the data set, you also want the discriminator to be unsure about which style it is. Basically output like values of probabilities for each style, basically evenly. That way you get art that can't be classified into all the known styles, but simultaneously does look like art.
Yeah.
How do you get the adversarial to like know art?
So I mean, you train it mostly under the same conditions. Like you have your generator that creates art from random noise vectors, then you have your discriminator that tries to determine whether it's real or fake. But it also just adds this extra thing where it tries to classify it into a set of classes. And then finally, this is the paper that we showed at the very beginning, where they were able to show these really high resolution interpolations between faces. So the basic idea behind this paper is that they were able to grow the GANs, I guess, as they trained. They started out with really, really small networks, basically like the random input, and then they'd have the the first layer of a generator, which would output like 4x4 images, 4x4 pixel images, and then from there they train that through the data set, which is really easy because the images are really small, and then they would upsize it to 8x8, and then they train that through the data set. Then they'd upsize that up to 16x16 and so on, and they could just continually do this up until 1024 by 1024 results, 1000 by 24 by 1024 images. So you can see here. Also, I'd like to note that you can see at the bottom how much time it takes to go through this.
This is a very powerful GPU.
Yeah, so at 128 by 128, it took them 3 days to get a good result.
That's scary.
So slowly zooming in. And finally, they reached the highest resolution that they were going for. And basically, this is like one of the few papers that were able to achieve like what is megapixel resolution generated outputs, and it's pretty amazing. In fact, I think they had a demonstration where they tried to train directly to 1024 by 1024, and it actually took a lot longer to do it without progressive growing. So this technique that just came out a month ago potentially has the chance to really change how GANs are going to proceed in the future. I think we're going to see a lot more papers that focus on growing GANs, growing GANs instead of trying to train them all at once.
Yeah. Are there any drawbacks to starting from like a 4x4 and then growing to high resolution?
I'm not sure. There's a lot of benefits, though, for sure. So clearly you can. It's really easy to learn 4x4 because it's so small, and the dimensions that you need to get to that point are like, yeah, exactly. And so this is actually a technique that they use pre-GPUs for just generally training. They do layer-wise greedy training for something like an autoencoder, which is like a simple network that maps to itself. And they were able to do this technique, and they were able to save a lot of computational time by doing it. And so, yeah, I think that there's a lot to say that it was very successful in the past, and that also if you can pose yourself as an easier problem at each step, it's probably like you can imagine it'll be easier to solve, and that's what I think the progressive growing really gives it. There's also one more section that I think is really cool. Yeah, so there's latent space interpolations of LSUN, which is a large data set that has just a bunch of different categories of images. And I think the interpolation ends up really cool, especially for the cat data set. So what they do is they just Google search a bunch of images, basically. And then the cats end up having like all the meme text in it. So you'll see that in a second. Actually, you can see it right here. The cats, it's going to move over. So you maybe see it generate like attempts at making the meme text. So yeah, there it is. Yeah. So I thought that was pretty funny.
Why was the text backwards?
Maybe they. Oh, you know what? They may have flipped it or something during training, just to
increase
get
the
like
data set size.
Exactly. Yeah. So what's next? As I mentioned before, GANs have gotten a lot of traction recently. Since the first paper came out in 2014, nothing really happened until like the end of 2016, and then it just grew exponentially. So it's clearly a very hot topic right now. In fact, there's this repo called the GANs do that has just like, I think every single, or it tries to get every single GAN paper that's been published on arXiv. So yeah, it's pretty interesting kind of catalog. You can see all the like funky names that that researchers have posed for their GANs. And it's a really cool field because I think that it has a lot of cool applications that still haven't been discovered yet, especially outside of like image processing. Yeah, so we leave you with a few papers to read. I'm not going to go through each one of them, but a few of them we've already mentioned. I think the very first one, the Goodfellow tutorial, it's from the original creator. He gave a tutorial back at the Neural Information Processing
Symposium.
Yeah, back last year. And it's a very good overview of just generative models, plus then GANs and everything afterwards. And then of course we have progressive growing of GANs. So I think these are all important. And then there's also interesting ones. So somebody mentioned, you mentioned that that you were wondering how we could like separate the features out of the individual features of the image out. So InfoGAN lets you do that, or you can like try to learn some features of an image in an unsupervised manner using a GAN by adding some extra kind of like info theory losses to your training process. And then numerics of GANs and on convergence, stability of GANs. They talk a little bit more about kind of the mathematics behind generative adversarial networks, which I think is super important for us to like understand how to improve them further. Because a lot of the time, it turns out that people just kind of throw shit at the wall and it works. And so it really feels like more of an empirical science rather than a mathematical one. And that's something that I think these papers try to improve upon. And then finally, the deconvolution and checkerboard artifacts. That's the stuff that we mentioned way at the beginning and also kind of in the demo as well. That's just the idea that you want to replace your transpose convolutions, the deconvolutions as we call them. Not the right term, still. Everybody calls it that. Yeah, so removing that and replacing it with this like upsampling and then conv from there just tends to be better. And it's not exactly a GAN paper, but it's still very relevant for like image-based GAN stuff. So those of you who want to get like a little bit more involved with GANs, I have a recommendation of a project that you could do. Very simple. Shouldn't be too bad, but I think it'll give you like a good understanding of like debugging GANs and so on. So first thing you want to do is make an AWS account. We have a guide on the on our in a GitHub repo that I've linked to here. So hopefully it's a little bit more a little less painless, or a little more painless. My bad. It is a very painful process. Or at least I've had that.
Is it expensive?
So that's the great thing. AWS Educate, which is like an educational platform from AWS, gives you I think $100 of credits. Which if you
usually like apply for training.
Well, yeah, I was about to say that. So
40 minutes?
What?
I heard
No,
40 minutes.
no, it's longer.
Like 4 days.
Well, so you can get like if you price it correctly, you can get it at like 40 cents an hour. So yeah, 40 cents an hour to figure that out. Yeah. Also, Google Cloud Compute offers 40 cents an hour GPUs, which is they're actually the identical same GPUs. The 40 cents an hour in AWS is a little bit more like a trick. You have to basically bid for it, and sometimes what will happen is bidding will jump all the way up to like $9, and you'll get kicked off of your instance. So Google Cloud Compute could be really good. My only hang up about Google Cloud Compute is they don't have good AMI systems. Basically, they don't have easy ways for you to transfer software across images, which is a pain in the ass. Yeah, whatever. Check it out on your own. AWS is so far, I think, the best option. Next thing you want to do is get an image data set. If you want the art data set, you can email me. My email is in the beginning. I have it in AWS right now, so it would take me maybe like a minute to transfer it to you. So, but otherwise you can check on Kaggle. Kaggle's always good for finding good image data sets and so on. Or you can try LSUN, which is from Princeton. Just look at the progressive growing papers, progressive growing GANs, like video, if you ever forget what the name is. And then what you want to do is grab DC GAN. I've linked to it here. It's just like a TensorFlow implementation, and then just train it. You literally just need to set up an image data set, like put it as a parameter, and then from there you're good to go. You just let it train and let it go for like a day, and then just see what the results are. If you get mode collapse, like if the output just becomes the same, then you can try looking at GAN hacks. Or if your discriminator just goes down to 0, then you can just keep looking at GAN hacks. And I think this is a good way to like play around with and get an intuition for GANs. Yeah. Any questions about that or anything else in the presentation? Otherwise, that's basically it. Cool. Thank you so much.
Attendance code.
Oh yeah. Hey, wait.